Hi everyone, welcome to the next video. This one's called Intro to Differential Equations. Here are the objectives that we're going to cover. This is an entire class at college that you would take. We called it DiffEQ. So this is just an introduction to differential equations. Of course, it comes right out of calculus. So a differential equation looks like this right here. The 2x y prime minus 3y equals 0. It's an implicit differentiation. So it's an equation that involves an x, a y, and then derivatives of y. So it's a derivative that's been taken with respect to x. And it talks a lot about differential equations are very useful in the sciences where we can model different phenomena like radioactive decay, population growth, and Newton's law of cooling. Now, Newton's law of cooling is what's used in forensics to determine, the heat that leaves a body, and then you can determine when that person passed away. And then I just found this online. I thought this was really interesting. These are differential equations that simulate airflow around an obstruction. So differential equations are going to be extremely useful. Functions represent the physical quantity. So the function itself, like the position function, it represents the physical quantity. If you take the derivative, that would be the rate of change. And then if the differential equation is the equation with the relationship between the two things. So the position and the velocity functions related together. So a function y equals f of x is a solution of a differential equation if the equation is satisfied with y and its derivatives are replaced by f of x and its derivatives. So for instance, here's the differential equation, y prime plus 2y equals 0. The general solution of this equation would just be the function y equals ce to the negative 2x, which you'll recognize as an exponential function with a base of e. And one particular solution, so for instance when c is 1, would be this equation right here. And so what we did earlier, we generated slope fields as a graphical representation of general solutions. So we used the derivative to generate the slope field, and then the slope field looked like all the general solutions with different numbers for c there. And then this other definition down here that's really important is that the order of a differential equation is the largest derivative present in the differential equation. So for instance, if I had y double prime plus 2y equals 0, y double prime, this would be the second derivative, and then, third derivative, and then fourth derivative. And so it's not y to the fourth, it would be the fourth derivative of x. And so generally that's what they use. So our first example is to determine whether the function is the solution of the differential equation y double prime minus y equals 0. And so first of all, we need to see if sine then would be representative. So basically what we're going to do is we're going to have the differential equation over here. And what we need are these pieces so we can substitute. So we know what y is. Y prime would be cosine x. Y double prime would be negative sine x. And so we put that in. Negative sine x is double prime minus sine x equals 0. Does it equal 0? No. And so this is not a solution. Now this one, on the other hand, if I take the derivative, because I'm still using the same thing, y double prime minus y. So if I take the derivative, that's going to be e to the negative x times negative 4. And then y double prime will be positive 4 e to the negative x. And so when I put that in there, 4e to the negative x minus 4e to the negative x, that does equal 0. So this is a solution. Now, c is a constant. C could be all the constants. It could be any constant. It doesn't have to be the same constant. So if I go ahead and take the derivative of this, I get ce to the x times 1. And then double prime would also be ce to the x, right, because c is just a constant. So I would have ce to the x minus ce to the x equals 0. Yes. So this is a solution. Now it's a general solution to the differential equation. So here's one that's a little more intricate. It says, is y squared minus 2 natural log of y equal x squared a solution of this this differential equation? And so if I go to use implicit differentiation to take the derivative, I have 2y dy dx, and it's using dy dx, so I'm using it, minus 2 over y dy dx equals 2x. If I factor out the dy dx, I get 2y minus 2 over y equals 2x. And I'm going to have to use a little bit of algebra here. So I have dy dx equals 2x over, and then to get a common denominator, I would have 2y squared over y minus 2 over y. And then, so that's both of them over y. So I would have 2x over 1 times y over 2y squared minus 2. And then, since all of that's multiplication, I would have dy dx equals 2xy over 2, y squared minus 1. The 2's cancel now because it's multiplication, both of them, and I end up with this. So yes, it is a solution. Yes. The general equation is a solution of the differential equation. Okay, so this on this one, we're going to use some initial conditions so we can find a particular solution of a differential equation. All right, we have that the second derivative of s, the position function, is negative 32. And we know it has a general solution, and if I could work it backwards, I would end up with the general solution for the function as negative 16 t squared plus c1, the first constant, times t, plus c sub 2. So we have two different constants because I had to integrate that twice to get back to the function. All right, if I've given some initial conditions, and I didn't just make these up, these were the conditions that were given, but it could be any. I would say that s of 0 at time 0, s of 0 was 80, and s prime of 0, the slope at that point, is 64. And so in that case, then my particular solution to the differential equation would be s of t equals negative 16t squared plus the first constant would be the first derivative, right, because that's the linear function. That would be 64t, and then plus 80. And so this would be my particular function that would still, when I took the derivative and took the derivative, again, would end up with my second derivative, which was negative 32. Okay, so on this one, we're going to verify that a particular solution, of a differential equation. All right, so this gives us the first derivative. This is my initial condition, and it looks like it changed it to a capital Y. That should be a small y. And then this is my general equation. All right, so I want to see if I can get to this using this. Okay, or find out. All right, so the first thing I need to do is take the derivative of it and double check that the derivative of this function is indeed my derivative that I have over here. So 6 minus 4 cosine x plus 0. So that's verified. Okay, then what I also need to do is I need to look at my function, my beginning function, and put in 0 for x. And see if that equals 1, which it does, so that is verified. That is verified. Okay, so let's do the same thing on this next one, right? I'm going to verify that this is the first derivative. So I would have e to the negative cosine x times the derivative of the exponent, which is going to be, right, the derivative cosine is negative sine, so negative negative is just sine x. So I have, it looks sort of, I'm comparing it to this. Once again, I don't know why it keeps randomly changing the capitals, but there you go. But notice here, what is y equal to? Well, y prime is equal to, this is y, sine x. So that is verified. That is a differential a solution of a differential equation. Okay, this one is. All right, so let's put in then the value that was given. So I'm going to go back to the original equation, y equals e to the negative cosine of pi over 2, right? And the cosine of pi over 2, I'm thinking over here, this is where a cosine is 0. So this is the same thing as e to the 0, which equals 1. So y of pi over 2 is equal to 1, and that also verifies the particular solution. So this is, so the function is a particular solution. So we're going to do more of these in class. So I hope you took good notes, and I will see you then.